We're going to talk some more about the four fundamental subspaces, which I started talking about last time. So we have an M by N matrix, which is a map from Rn to Rm. And the null space of A is a natural subspace of Rn. And the image of A is a natural subspace of Rm. So those are two very natural subspaces associated with A. And then we look at the transpose, which is an N by M matrix going the other way, and then the null space and the image are switch sides. The null space of the transpose is over here, and the image is a subspace of Rn. And that's it. Those are the four fundamental subspaces associated with a matrix. So that's pretty much what I talked about last time. Let me say a little bit about some terminology here. So the image of A, another word for that is the range of A. That's just a synonym. And the null space of the transpose is the left null space of A. So in the book it uses this terminology. So what do I mean by the left null space of A? Well, we have this M by N matrix A, and the left null space is the following. It's where you put the vectors on the left, which is to say you have a matrix multiplication like this. You have a row vector x1 through xm, and you multiply it on the right by this M by N matrix, and you get the 0 vector of size n. So that's the left null space of A. But if you think about it for a second, that's just the same thing if you take the transpose. That's where you'd multiply on the right and get the 0 vector. So the left null space of A is exactly the same thing as the ordinary or right null space of the transpose. Okay, here are a couple of facts about these, and this is bringing in the column and row spaces. The image of A, we've seen, is the column space of A. All right, and similarly, the image of A transpose is the row space of A. Well, the image of A transpose is just the column space of A transpose by the first statement, and the column space of A transpose is indeed the same as the row space of A. So that brings the row and column spaces into the picture. The next thing is to talk about the dimensions of these various subspaces. We've already talked about this a little bit, but we'll give some more detail here. So the main point is that if A is a matrix and you put it into row echelon form, well, the matrix A and its row echelon form, the dimensions of these various subspaces are the same. That is to say, if you want to compute them, if you compute these dimensions for A, or you put it in row echelon form, you get the same answer. So we may as well assume that we've put A in row echelon form. So that looks something like this, for example. And let's look at the dimensions of these various spaces for such a row echelon matrix. Well, first of all, what's the dimension of the row space of this matrix? Well, that's clearly the number of pivots, because there's one row for each pivot, and each of those rows are linearly independent. And that number is, which will denote R, is the rank. Now let's look next at the dimension of the null space of A. Well, we know what that is. It's the number of free variables, and that's these columns over here, and there are n minus the rank of those, n minus R of those. Okay, so we've seen all of this before. Now, what about the dimension of the column space of A? Well, it's the number of pivots, and there's one column for each of these pivots right here, and there are a bunch of other non-zero columns further to the right, but those are all linearly dependent. So the dimension is again the rank. And finally, the dimension of the null space of A transpose, well, you just flip the matrix, and instead of n minus r, you get m minus r. Now, as always, I really like to think purely in terms of null spaces and images. So 2 and 4 are given by the null spaces of something, and 1 and 3 are given by column and row spaces. Well, we can replace those with the image of A transpose and the image of A. Okay, let's put all of this together into a theorem. So we have an m by n matrix A, and let's call its rank R. And remember that the rank of A is the same as the rank of A transpose. Then the dimension of the image of A is equal to R, the rank. And next, the dimension of the image of A transpose is also the rank. And next, the dimension of the null space of A, well, we've seen that's n minus r. And just flipping the thing around, we see that the dimension of the null space of A transpose is m minus r. And let me reiterate that there are really only two facts here, 1 and 3, and 2 and 4 are just facts 1 and 3 applied to A transpose. Okay, so I think it's helpful to draw a picture. This is going to be extremely rough and shouldn't be taken too literally, but I think it gives an idea of what's going on. I have this n-dimensional space Rn, and in there's an r-dimensional subspace and an n minus r dimensional complementary subspace, and over in Rm there's two blocks of size r and size m minus r, and A transpose, they both have image of size r, whereas A kills this n minus r dimensional space, and A transpose kills this m minus r dimensional space. So that shows the kernel and the image in some sort of crude picture. Again, don't take that picture too seriously. It's just sort of an idea. Another way, I think, to cement these ideas is to look at an extremely simple example. Let's look at the following row echelon matrix, absolutely the simplest thing you can have, which is it's 3 by 3 identity matrix in the upper left-hand corner, and everything else is zeros. So this is a 5 by 8 matrix, which is to say it's a map from R8 to R5. And let's look at these various subspaces in this example. Well, the map, it takes x1 through x8 to what? Well, it keeps the first three variables and then sets the last two equal to 0. And so the null space of A is these 5 variables, x4 through x8, which is to say it's 5-dimensional. And the image of A is these 3 variables, which is to say it's 3-dimensional. And 5 plus 3 is indeed equal to 8, which is n. And going in the other direction, the transpose takes y1 through y5. Well, it just keeps the first 3 and then sets the remaining ones equal to 0. So the null space of A transpose is these 2 variables, and the image of A transpose is these 3 variables. And 3 plus 2 is equal to 5, which is m. Now, just a little warning here. This is an extremely simple example, and it's a little bit deceptive. It's not, in general, that A and A transpose map these spaces to each other in such a simple way. But what is true is that the dimensions really work out this way. So don't take the subspaces themselves too literally, but think of this as just giving you information about the dimensions. Okay, we're going to go on and talk next about left and right inverses of matrices. So let me remind you about inverses. So let's do the square case first. Suppose you have an n by n matrix. So it's a map from Rn to Rn. And the inverse is a map going the other direction. And it satisfies if you take a vector and go this way and send it to AV and then come back by applying A inverse, you get V again. And going the other way, if you start by applying A inverse and then apply A, it takes V to itself. And that is to say, A times A inverse is the identity, and A inverse A is the identity. And those are the left and right inverses of this square matrix, and they're equal. And everything here is square of n by n. Okay, let's look at the same thing for a rectangular matrix, m by n. So it's a map from Rn to Rm. Call it A, and let's write L going in the other direction. And what this is supposed to satisfy is you send V to AV and then back to LAV, and you're supposed to get V again. So that's the left inverse. And I'll write the right inverse as going again from Rm to Rn, but now if you apply R first and then A to that, we're supposed to get V back again. So this here is the left inverse, and over here this R is the right inverse. And both of these are maps from Rm to Rn. So that is to say L and R are both n by m matrices, matrices of size n by m. Okay, let's look at what's going on a little bit in terms of matrices. So I have this m by n matrix, and I'll emphasize that it's not square. And what does it mean to have a left inverse? Well, I want to multiply it on the left. So I have to multiply it on the left by a matrix of this size, n by m, so the m's cancel, and you get an n by n result. And we want this matrix to be the identity. And similarly, if you multiply it on the right, it has to be a matrix of this size so that you get an m by m identity. So filling in these matrices, we see that L times A is the n by n identity, and A times R is the m by m identity. And the question is, how do you tell whether these matrices L and R exist or not? So in the square case, of course, the issue is the determinant has to be non-zero. So let's look. So suppose I ask for the existence of the left inverse. LA is the identity on Rn. What that means is I send V to AV and back to LAV, and I'm supposed to get V again. And in the other direction, the right inverse is supposed to go like this. If you send, this is supposed to give the identity on Rm, which is to say you send V to RV and back to ARV. So that was just a recap of what I'd said before, but now let's ask, does L exist? So let's see, A maps this space Rn to a subspace, the image of Rm, inside Rm, and L is supposed to take the image of A back to Rn, and you're supposed to get all of Rn, because you're supposed to get every vector back again. And so how can L take the image of A back to Rn? Well, the image of A had better be n-dimensional, or else there's no hope. So how can that be? Well, the image of A the dimension of the image of A is supposed to be n, but remember that's the rank. So the rank is supposed to be n, and remember that the rank is less than or equal to both m and n. So if the rank is going to be equal to n, you'd better have that n is less than or equal to m. Okay, let's look at the other direction. Does R exist? So let's see. If R is going to exist, we have this map from Rm to Rn, and the image is R, and then A is supposed to take the image of R back to all of Rm. Well, that says that the image of A is all of Rm. That says that the rank of A had better be equal to m. And so that's clearly a necessary condition. And again, since the rank is at most m and n, this can only hold if m is less than or equal to n. So the conclusion of all of this is the following. We have an m by n matrix, and we want to know if it has a right inverse, which is to say a matrix satisfying this. Then the right inverse exists if and only if the rank of A is required to equal m. And in the other direction, the left inverse exists. It satisfies this. It exists if and only if the rank of A is equal to n. And again, I'll remind you that m has to be less than or equal to n, or n has to be less than or equal to m, appropriately. And how can they both exist? Well, m has to be less than or equal to n, and n has to be less than or equal to m. So you must have that m is equal to n, and that's equal to the rank. And for a square matrix, that's correct. The rank is as big as possible, is the same thing as saying that the determinant is non-zero. So let's draw this in terms of matrices. I think it's quite helpful to think in terms of matrices. It's a little more elementary, and it kind of helps to see what's going on. So to have a left inverse, I'm saying that m has to be bigger. So the picture is this. I have an n times an m matrix. I'm supposed to be getting the identity of size n. And this matrix here is A, and this matrix over here is supposed to be L. Well, you put A in row echelon form, and then you take L to be this matrix. And you see that the product of those two matrices is indeed the matrix, the identity of size n. Similarly, how can you have a right inverse? Well, in this case, n is bigger, so I'll draw it this way, m by n. And you're multiplying on the right by an n by m matrix and getting the m by m identity. And how does that happen? Well, in this case, A is over here, and you put it in row echelon form with anything over here on the right, in the right half of the matrix. And you take R to be this. And then the product is the m by m identity. Okay, that's a good place to stop. I'll see you next time.